Hey everyone, so this is lesson 4.1, Algebra 2. So today we're going to be talking about describing sets of numbers. And so our goal today is to be able to read, write, and understand inequality notation, set builder notation, and interval notation. So interval notation is going to be the most common one that we use. Inequality notation is probably what we're most familiar with, and then set notation is a bit more formal way of describing sets of numbers. So our essential question is, what are all the different ways that we can describe an infinite set of numbers? So when we talk about sets of numbers, one of the things that we run into is that a lot of times those sets of numbers are infinite, and there's no way, if I were to try to list out all of those numbers, like, it just simply wouldn't work. There's no way to do it. So instead of listing them out, we actually come up with a description of them. And so these three methods here are the most common ways of describing sets of numbers. So before we start describing sets of numbers, I just wanted to take a second to just review the types of numbers that we're talking about. I do have a separate video on our Canvas page that walks through the different types of numbers. What we're really concerned with is the real numbers. Okay, the real numbers encompass most of the stuff that we're going to do. We will talk about imaginary or complex numbers, but we'll kind of cross that bridge when we come to it. Right now, we're describing all the real numbers, and just remember that the real numbers are made up of all these sort of subsets of numbers. So we kind of look historically back. The very first numbers that humans started talking about were natural numbers. Those are the numbers that you could look at something and count it and see it. There's a visual representation of it, and they're very easy to understand. So the numbers 1, 2, 3, 4, 5. The natural numbers do not include 0, do not include negative numbers, do not include any of the numbers in between those numbers. So it doesn't include decimals or fractions or anything like that. Okay, so just the things that you can see and count are the counting numbers. And then quite a ways after counting numbers were established, the concept of using 0 as a number came about, and there was actually a mathematician from the Middle East, what's his name? Al-Khwarizmi was his name, Muhammad Al-Khwarizmi. Anyway, he was the one who kind of not first, but one of the first people to kind of popularize the use of 0 as an actual number. The Romans don't have, like, Roman numerals. There's no representation for the number of 0 in Roman numerals, and so we get into the sort of Arabic numbers, right? The traditional numbers that we know today, and we include that number 0 in there. And in the history of humankind, that's a pretty recent development. I think that was around the year 800, the Common Era, the BC, AD. All right. So, and then after the whole numbers, then we talk about the integers. The integers include the negative counting numbers as well. So again, that concept of a negative number was fairly new in terms of mathematical in the mathematical world. That the idea of that, I'm in debt or I owe you something was very common, and the negative numbers actually came as a result of that. So if I had 5 chickens and I owed you 8 chickens, then I really didn't have 5 chickens. I actually had a negative 3 chickens, right? I had less than 0 chickens. I owed somebody chickens. So anyway, the concept of negative numbers really came out as a part of commerce. And then we start talking about the rational numbers. The rational numbers are just any numbers that can be written as a fraction. So the numbers that are in between the integers, and not just the numbers that are in between, but the numbers that can be written as a fraction that are in between. So anything that can be written as an integer divided by another integer, we call that a rational number. We can represent rational numbers as decimals. We can represent them as fractions. Sometimes we can represent them. So, for example, 1/3, if I represented that as a decimal, it's 0.33333, and that 3 repeats forever. And that's okay. I can represent that as 1/3, even though I can't get an exact value as a decimal representation. It's still considered a rational number because it does repeat, and it can be written, in that fractional format. There are some numbers, though, that can't be written like that. And we call those numbers irrational. So irrational are the decimal numbers that can't be written as fractions. So these are decimals that don't repeat and they don't end. And usually, there's some sort of mathematical symbol or representation that we use for those. So a really common example there is pi. So pi is 3.1415, and it goes on forever. It never repeats. It never ends. And they've calculated that out to millions and millions of places, and there's no repeating digits in there. There are lots of other constants like that as well. Pi is probably the most familiar, but there are lots of other numbers. E for Euler's number. A lot of Greek letters, phi and phi, and golden ratio, and things like that. The other kind of irrational number are roots. So the square root of 2, for example, is an irrational number. If I calculate, a number that's multiplied by itself and gives me exactly 2, it's not a rational number. I can't write that out as a fraction. And if I do that calculation, that decimal place just keeps going on and on forever and ever, never repeats, never ends. So those are irrational numbers. And so that brings us to the real numbers. The real number is just the set of all those. It's just a collection of all those types of numbers. So if I'm talking about real numbers, I'm talking about all the irrational numbers and all the rational numbers. Okay? The irrational numbers and the rational numbers. When I'm talking about the rational numbers include the integers, and the integers include the whole numbers, and the whole numbers include the natural numbers. So we have these subsets of rational numbers, and then we have the irrational numbers, and then we have the real numbers, which are a set of all of those numbers. And as I mentioned before, there's another set of numbers here called the imaginary numbers or complex numbers. Those are numbers that kind of crop up when you're doing mathematical computations, but it's difficult to say this is what it represents. There's actually a whole field of study that goes into complex numbers and the complex number plane, and if you've ever looked at like fractals, or say like the Mandelbrot set, the Mandelbrot set is actually a plot of complex or imaginary numbers. And so anyway, so those are another set of numbers, and we'll actually come across those here actually pretty soon. So there's kind of a Venn diagram of all that. So it looks at the sets of numbers, and so we have real numbers, and we have imaginary numbers, and then that makes up all the kinds of numbers. Imaginary numbers, we have these purely imaginary numbers, and then they also say, well, complex numbers, I can actually write a real number as a complex number as well. And so we'll actually talk about some of that, but really what we're focused on right now is just the real numbers. Okay, so when we start describing sets of numbers, there's some different notations that we can use, and the three most common are an inequality notation, interval notation, and then the last one is a set builder notation. So inequality is probably what you're most used to. It's kind of what we're taught in middle school and so forth. We talk about inequalities. We use these less than or greater than symbols. We have compound inequalities, where we string together multiple sets of numbers. And interval notation, this is the new one, and this is where we're really going to focus our attention in Algebra 2. We're going to use interval notation quite a lot. It's just a more compact way of doing it. It's way easier to type. And it's a very shorthand way of discussing large groups of numbers or large sets of numbers. And then the last one is set builder notation. Set builder notation is a very formal way of discussing a set of numbers. So, we talk about this notation here, and it reads a very specific way. So the curly brackets mean a set of numbers, and then this part here tells us how to find those numbers, right? And then the second part tells us what the limitations are on those numbers. So this reads a set of all numbers x such that x is an element of the real numbers. Okay, so that's how we would read that. Again, very formal definition, but really all we're talking about there is all the reals. Okay. And so we'll talk some more about these as we move forward. But the interval notation, like I said, is the most important one for us to focus on right now. I do have a video out there and a link to a website that talks more about set builder notation. We're not really so much concerned with writing set builder notation, but being able to read it. So sometimes you'll see this set builder notation used in textbooks or in problems, and we just want to be able to read that and understand it. The whole area of writing and constructing sets using set builder notation it's a whole separate area of mathematics, and it can get very involved. We're not going to go down that path. We just want to be able to understand the basics of it and be able to read and interpret these things. Okay, so when we talk about interval notation, really what we're saying is we're saying all the numbers between these two numbers. Okay, so we give the smallest number it can be, and we give the biggest number that it can be, and we're including all of the numbers that are in between those two numbers. So the smallest is always first, the largest is always second. They're separated by a comma, and then we use some brackets to kind of clarify what we mean. So if I say that I'm looking for all the numbers between 5 and 10, say, or actually down here, all the numbers between -5 and 2. Look at that example. The way that we would write that in interval notation is we would say, well, the smallest number this could be would be -5. And the biggest number it could be is 2. Okay, so we go -5, 2. And then we would decide what kind of brackets we need to put on those. So right here it says that it can include -5. So if it includes -5, I want to put a square bracket on that. But it does not include 2. So it can go right up to 2 but not be equal to 2. And so we would put a round bracket on there. Okay, if we were looking at a graph of this, right, this was -5, and this was 2 up here, and 0 is going to be somewhere around here. If we were to look at a graph of that, we would have a solid dot right here, right on the 5, and we would have an open dot, an open circle there, and then we would say all the points in between that. So in interval notation, that's how we say that. That square bracket is the equivalent of a closed circle there. The round bracket, right, we call that an open bracket. The round bracket there is an open circle. Okay, and so you'll hear those referred to sometimes. They'll say a closed bracket or an open bracket. That's what those mean. The square or the round ones. Okay, if I look at this next example, all the numbers less than or equal to 3. So as an inequality, I would write that like that. Okay, as a graph, I would write that, as here would be 3, and less than or equal to, so I'd put a solid dot there, and my values would be to the left of that. In interval notation, we'd look at the left side of it, so the smallest it could be. Well, there is no smallest, and so we're going to use the infinity symbol, and we're going to say -infinity to represent that left side. It goes on to the left forever. And then it can be, the biggest number it can be is 3, +3, and it can be equal to 3. Okay, so we'll put a square bracket on the 3, but then the infinity symbols always get a round bracket or an open bracket. And the reason for that is that infinity is not a number, right? It's more of a concept or a construct. And so this is just used to indicate that it's going forever in the negative direction. It's never going to be equal to infinity, right? You can't say that anything's ever equal to infinity. So we use that round bracket to say it's going in that direction. And then the last one, all of the real numbers. So, it's an inequality, we might say that, R for all the reals. On a number line, it would just be all the numbers on the number line, right? So like a graph of that really would be kind of ridiculous. It is the actual number line. But in interval notation, we would say, well, the smallest it could be, well, there is no smallest. And so we would say negative infinity. And then for the biggest number, well, there's no biggest number either. And so we would just say that that's positive infinity on the right-hand side. Okay. And sometimes you'll see it written with a positive there, and sometimes without. If there's no positive there, it's assuming that it means to the right. If you mean to the left-hand side, you should put it to the left. You would never ever see a positive infinity on the left-hand side of an interval notation, and you would never ever see a negative infinity on the right-hand side of a notation. So negative means to the left, positive means to the right. Okay. And then we always use the round brackets or the open brackets. Okay. In MyOpenMath, when you go to type infinity, the way that they want you to type that is just with 2 lowercase o's. Okay, not 0. Right? It'll interpret that differently, but if you put 2 lowercase o's right next to each other, it will interpret that as infinity. And so if I type in negative OO, that would be negative infinity, or just OO or positive OO would mean positive infinity. So some quick examples here. If I were to look at this set of numbers, if I were to write this as an inequality, this would mean all the numbers less than -1. So I'd say all the numbers, and I'd use x or some variable there that are less than -1. Can't be equal to -1 because we've got an open circle there, and it goes on forever to the left. And so in interval notation, I would say the smallest would be negative infinity, and my biggest would be -1. Infinity gets our open bracket or round bracket, and because this is an open circle here, we'll use an open bracket or a round bracket there. Here we see some set builder notation, and so we want to read this. Really, what we're looking at is this part of it, but the way that we would read this is we say the set, right? The brackets mean the set of all numbers x, such that, that's what that little bar means, such that that x is between -4 and 3, right? Where -4 is less than or equal to x, and x is less than 3. Okay, so here we have a compound inequality. If I were to graph that, I would say, let's say that this is 0 here, and so 1, 2, 3, 4, this would be -4, and 1, 2, 3, this would be 3. So from -4, I would have a closed circle, and +3, I would have an open circle, and then it would include all the points, all the numbers in between those two. If I were to write this in interval notation, it would be simply -4 to 3. Because it can be equal to -4, I'm going to put a square bracket, and because it can't be equal to +3, I'm going to put a round bracket or an open bracket. So write this set of numbers using interval notation. So this is all the x is greater than -5. If I were to look at a graph of this, this would be -5. I would have an open circle, and my graph would go on forever to the right. So interval notation, the smallest number it can be is -5. The biggest number it can be is infinity. Round bracket on the infinity, and I've got an open circle here, so I'd use a round bracket on the -5. Interval notation is a really handy way of doing it. Once you kind of get used to the symbols and the and writing it out, it really is a really simple and effective way of talking about a large group of numbers. Okay, and the last one here, So this is a really typical sort of thing. You'll be asked to solve an equation, work a problem, or something like that. But then they want you to write the solution using interval notation. So if I go through and solve this, I'm just going to solve it like I normally would. Subtract 1 from both sides. Negative 2x is less than or equal to negative 6. And then I'm going to divide by negative 2. Keep in mind dividing by a negative, right? So I have to change the direction of the inequality. So this is going to be x is going to be greater than or equal to positive 3. Okay, so there it is as an inequality. So in interval notation, I would say my smallest number there would be negative infinity, right? It goes on forever to the left. Sorry, I had that totally backwards there. Let's try that again. I think about the graph of this, right? X is 3. I'm going to the right. So my smallest number is 3. My smallest number is 3. And my biggest number is going to be positive infinity. It's going to go on forever to the right. And then round bracket there. And I've got a closed circle here, so I'll use this closed bracket or a square bracket there. That's not a very good square bracket, but you get the idea. All right. So in your assignment today, they're going to be asking you to kind of move back and forth between set builder notation, inequality notation, and interval notation. But again, our focus is to really understand and become fluent in using this interval notation. Okay, hope you have a great day.